This is the data sheet for the AVR 128 DA48, which is the one that we're going to be working with. And as you can see from the, let's see here, does it say on here? It's, I want to say 684 pages, but everything you could possibly want to know about this microcontroller. It's from the AVR family, which was introduced by the Atmel Corporation back in the 90s, I believe, but Atmel was bought out by Microchip in, when was it, 2016? Yeah. So Microchip has it, and they've continued the evolution of the AVR family of microcontrollers. Just an overview of the processor. The DA family uses the AVR CPU and with hardware multiplier, running it up to 24 megahertz with 128 kilobytes of flash memory, 16 kilobytes of static RAM, 512 bytes of EEPROM, and 48 pin package. That sort of thing. It has a lot of built-in peripherals on it. It's the AVR 128 flash size in kilobytes. DA is the family, which has the which is a certain configuration of peripherals that it has, and the 64 in this case is the pin count of the microcontroller. The one we're going to be dealing with is the 48 pin version. Some statistics for it. We're going to be using from this column here. Peripheral overview. What does this microcontroller have? Well, we're going to be in this column here, 128 DA48. It has two 16-bit Type A counters and four 16-bit Type B counters and one 12-bit Type D counter and one real-time counter. These peripherals will be described in more detail as we go along. The USART stands for Universal Serial, Universal Synchronous or Asynchronous Receiver and Transmitter. That's a serial port, similar in nature to the RS-232 standard that has been around for years and years and years. SPI is another serial port interface. SPI it is another serial connection. Two-wire interface, I2C, is another type of serial connection. 12-bit differential ADC. ADC stands for analog to digital converter. It can take an analog signal and convert it into numbers for you. 12-bit resolution. 10-bit digital to analog converter. So it can output an analog signal with 10 bits of resolution. analog comparator, zero cross detectors, peripheral touch controller, custom logic, watchdog timer, various other things that we're not going to worry about. Let's see here. General purpose input and output. Of the 48 pins, 41 are can be used for general purpose input and output. Basically, you put a high signal on one and a low signal on another, and can control other digital devices that way. The ports are arranged in 8 bits. Port A from 0 to 7, pin 0 to 7. Port B is only from 0 to 5. C and D are 0 to 7. PE and PF are limited as well. All 48 general purpose I/O pins can be used as external interrupts. You can use each of the pins. You can configure the pins individually to be interrupt triggers. Let's see here. There's more of an overview. Here's the features. I don't know why this isn't on the first page, but the CPU runs it at 24 megahertz up to 24 megahertz. The clock is selectable. Single cycle input-output access. So you can access the input and output peripherals in a single clock cycle. A 2-level interrupt controller. 2-cycle hardware multiplier, so multiplications are done fairly quickly. Supply voltage range, pretty wide range, from 1.8 volts to 5.5 volts. Again, 128 kilobytes of in-system self-programmable flash memory for the program memory. 16 kilobytes of static RAM for using for local variables and temporary data storage. In laptop terms, your EEPROM is like your hard drive, what you could write to, and you lose power, you won't lose that data. The user row and all that sort of stuff we won't worry about. The endurance, flash and EEPROM are they wear out after a while, so these you can reprogram these processors up to 10,000 times. EEPROM 100,000 times. Most of this stuff you can basically skip over or read it through if you want to in your spare time. Let's see here. Let's get to the let's see here. Table of contents. Let's go to the memory overview. Well, let's see here. Yeah, let's go to the memory overview. Oh, that was what we did. No, that's not the. Come on. That was before the features. The block diagram, that's what I was looking for. This is the block diagram of the computer. The AVR CPU is here. They use a lot of acronyms. They have the various peripherals. This will make a little bit more sense for as we go along. But it has the memory data bus, the data bus for the for various internal peripherals, input-output data bus for the general purpose registers and the ports to the outside world. Program data flash, program data flash memory data bus. Yeah, it's it'll take a little while to get used to the all the acronyms and all that sort of stuff. I know it can be a little bit of overwhelming at first, but it'll make sense to you as we go, more sense to you as we go along. Let's see here. Let's see here. That's it. That's a. Whoops. Let's look at the well, let's go back to that. Let's see here, the memory map. How memory is organized. Come on. CPU. I guess it's the. Come on. This is not as easy to jump around as using here we go, the memory map, using Acrobat. Okay. I/O memory. Basically, this has this architecture, being Harvard architecture, has two memory maps. How the memory is organized. One from 0 to 1FFFF is your flash memory. That is your program memory, where the program you write is stored. Now the program counter or PC, when you first turn it on, it equals 0. and it executes instructions in order as the program counter increases. Each step in the each instruction will increase the program counter 1 after the execution of that instruction, unless it is a branch or a jump type of instruction, in which case it will load the program counter with the address it's jumping to. But the program counter keeps track of where everything is in, or keeps track of where you're executing in the flash memory space. The data space is broken up into different segments, as you can see. The I/O memory, single cycle I/O registers and extended I/O registers are at the base of the memory space, and they are all addressed the same way. So it is while the static RAM and the EEPROM are different areas, and on the block diagram you'll see they're in different blocks and different sections of the processor chip. They use the same addressing scheme. So the addressing is all done with typically with load and store operations. Access data memory. Load and store operations. It's just broken up into different segments of where the data looks. The I/O registers are the registers that control the peripherals. They are memory locations that the peripherals look to know how to behave. So you write or store to those locations, and the peripherals will behave a certain way. To determine what is going on with a peripheral, you can load from those registers and interpret the data accordingly. So those are the addressed in the same way on the same map as the data space, and that goes up to from 0 to FFFF. We won't get into the in-system reprogrammable flash memory, where you can change the program during operation. But that's the arrangement of the memories in this Harvard architecture microcontroller. Let's see, and go back there. Okay. Let's see here. This is a RISC architecture CPU, which is reduced instruction set computer or computing. Because of that, the instructions, more often than not, execute in one clock cycle. A complex instruction set computing processor, you can take 20 or 30 clock cycles per instruction. In this processor, most of the instructions are single clock cycle instructions. So you can get a throughput of 24 million instructions per second, which is not really fast, but for a processor the size of my fingernail on my pinky, that's pretty snappy. But now the let's see here. My notes are not as organized as I would like them to be. Let's see here. Those instructions fall into 4 categories. ALU operations, bit manipulation, branching, and moving data. All the instructions the computer knows how to do fall into one of those 4 categories. That's just about any computer. But the I think it's 124 different instructions for this processor fall into one of those 4 categories: arithmetic and logic, bit manipulation, branching. Bit manipulation is changing the bits in a register individually. Branching, jumping from one point in the program to another. And moving data, whether it's between registers or in memory space or one of the I/O registers. So all the instructions fall into one of those 4 categories. The ALU takes care of arithmetic, bit manipulation, and logic. So, and this is add, subtract, multiply, and divide. Logic, will do and, or, not, invert or not, XOR, And bit manipulation is just setting and clearing bits. Setting is putting it to 1, and clearing it is setting it to 0. So the ALU has direct access to 32 registers. It cannot directly manipulate the, and that's to clarify, working registers. 32 working registers. The ALU cannot directly manipulate the data in the I/O registers or in the data space in the static RAM. It can only work with what's in the working registers. So to manipulate the peripheral control registers, you have to load the information into, load the data into one of the working registers, do whatever manipulation that you're going to do, then store it back to the register, peripheral register that you're trying to control and manipulate. One thing that helps with operations, the ALU operations, is the status register. Or SREG. Now the status register is located at memory location 0x3F. That will be useful memory location to remember. The status register is one register of 8 bits, and each bit has a certain meaning or use. The C bit, bit 0, is the carry bit. The carry bit is set when there is a carry in the previous ALU operation. So if there is a number greater than 255 as a result, this bit will be set, because an 8-bit register can only hold numbers up to 255. So if you add 200 and 200, this bit will be set, and you can see that from the result, the result doesn't make a whole lot of sense, because it will roll over and become a what it would appear to be a negative number. The 0 flag. It is set when the result of the previous ALU operation is 0. Simple as that. So a common thing to do is compare two registers, say R16 and R17. And what that does, what the compare instruction does, is it subtracts 16, the value in R17 from the value in R16. If the result is 0, then you know that the two values are equal. So it's used in compare operations to see if your result is 0 or if it's if the values are in fact equal. Bit 2, the N bit, the negative flag. The negative flag is set when there is a negative result in the ALU operation. So you subtract 6 from 4, that negative bit will be set, and you will know that the result in the register after the operation is a 2's complement negative number. Bit 3, the V bit, is the 2's complement overflow. It is set when there is an overflow in the arithmetic operations that support this. It's cleared otherwise. So if you subtract 200, negative 100 from negative 100, you would get a negative number that would overflow the possibility, because a 8-bit 2's complement can only go down to negative 128. So the 2's complement will show that there's an overflow and the data may in fact be invalid. The sign bit, or the sign flag, is N exclusive OR with V. Now what does that mean? If the negative flag and the 2's complement flag are the same, then the result is not a negative number, not a valid negative number, or it's not a negative number at all. The S flag will be set if the result is a valid negative number. If you have the result being something that you can use. Bit 5, the half carry flag. This is, I've never used this flag myself. It is set when there's a carry from the least significant nibble to the most significant nibble. So if there's a carry from the lower 4 bits to the higher 4 bits, this flag is set. That is used for binary coded decimal math operations. Exactly how, I'm not sure. It's not very commonly used, but they had the space in the register, so they added that as a flag as a flag. Bit 6, the transfer bit. The transfer bit is just a 1-bit memory location that you can store 1 bit of information. It doesn't do anything. It doesn't respond to any ALU operations. It's just there to as an extra bit to read and write from. I would personally use this in while loops. While the T bit is set, go through the loop, and at some point that T bit is cleared, it would exit out of the loop. So it's like it can be used in that way, but it's just a bit used for single bit storage. Now, the I bit, global interrupt enable. The global interrupt enable bit is the bit that enables interrupts throughout the entire device. If this bit is cleared, no interrupts can be triggered. If this bit is set, then interrupts can be configured and used. Otherwise, they are ignored. So we'll see when we get into more interrupts, more about interrupts, how you need 3 signals to trigger an interrupt. One of them is the global interrupt enable bit. Has to be high. The condition that the individual interrupt has to be enabled, so that has to be high. And then finally, the condition that the interrupt is looking for has to be high. So it's those 3 conditions to trigger an interrupt. And let's see here. I want to say that would be about it for the day, but keep these bits in mind, and we will get more into the instruction set, how the instructions work in the processor on Friday. Have a good day.